In section 2.7, we're going to review some properties of the periodic table that you may have learnt about in Chemistry 100, and also look at some new properties of the periodic table. So when we first start chemistry, we see the periodic table everywhere. That's because it's really useful. And fairly soon, you guys are going to become quite reliant on your periodic table and are going to want to have one handy most classes. So where does the periodic table come from? Well, in the 18th and 19th century, there were a lot of new elements discovered, and it became hard to kind of keep track of everything. And so people recognized that there was a need for a system to organize the elements. There were a variety of systems that were proposed, but it was the one developed by Dmitry Mendeleev that ultimately won the popularity contest. So the Russian chemist Dmitry Mendeleev, he organized the elements such that elements with similar chemical and physical properties were placed next to one another. So he had a whole bunch of cards and he had all of the properties of the elements written on them, and he just kind of organized these on his desk so that the ones that were most similar were placed near one another. He didn't know anything about subatomic particles at this time, but what he was actually doing was placing the elements in order of increasing atomic number. One of the interesting things that Mendeleev noticed was that after a series of elements, the properties would repeat. Mendeleev also left a bunch of gaps in his table, and this was where there was a sudden jump in properties. And what he proposed was this was where there was an element that had yet to be discovered. In addition to leaving a space for these undiscovered elements, he also predicted what their physical and chemical properties would be. And he was pretty good at doing this. For example, Mendeleev predicted that there should be an element with properties similar to aluminum, so he left a gap next to aluminum. He called this missing element Eka aluminum. It took 17 years after the development of Mendeleev's table for people to find this element, and when they did, they called it gallium. And it's quite amazing how the experimental properties of gallium line up with what Mendeleev predicted. For example, Mendeleev predicted that gallium, or what he was calling Eka aluminum, would have a low melting point. It actually has a melting point just above room temperature of 30 degrees Celsius. You can melt it in your hand. Mendeleev predicted that gallium would have a density of 5.9 grams per centimeter cubed, and he was right, that is the density of gallium. He also predicted that gallium, when it reacted with oxygen, would form a compound in which two gallium atoms combined with 3 oxygen atoms. And you guessed it, he was correct. So the cool thing about Mendeleev's table is because elements are placed near elements that have similar properties, we don't really need to memorize the properties of all of the elements anymore. We just need to know how the properties vary across the periodic table. So for example, if I'm looking for a gas, I know that all of the elements in group 8A are gases. Later on we will see that all of the elements that are metals are on the left of the periodic table, and so on and so forth. So there's a bunch of properties where we just need to know the pattern of how these things vary across the periodic table, and we don't have to remember anymore the individual properties of the elements. So in the periodic table, every element is assigned to a row, or what's called a period, and most of the elements are also assigned to a column, or what we call a group. Those groups that have A's in their names, and there's 8 of those, they're referred to as the representative elements, and they're the ones that we're going to mostly focus on in this class. Elements that are in the same group have the similar properties, and that's important to keep in mind. Those groups that are in the central part of the periodic table that have a B in their group designation, they're referred to as the transition elements. There are 2 rows that are normally placed underneath the periodic table. They don't have a group number, and they are referred to as inner transition elements. There are 7 rows to the periodic table, labelled 1 through 7. And it's always best to label these on the right-hand side of the periodic table if your periodic table doesn't have these included. And something important to recognize is that elements 58 through 71 really should be up in here in row 6, and elements 90 through 103 should also really be up inside the main body of the periodic table in row 7. But they pull these two rows out and push the ends of the periodic table together to save space and to make the periodic table fit nicely on an A4 page. So when you are numbering these periods, remember it goes 1, 2, 3, 4, 5, 6, 7, and then 6 and 7. So whilst elements that are near one another in the periodic table do have similar properties, we'll see much greater variation across a period between properties than down a group. So what I'm really saying is that, say, nobelium is much similar in properties to vanadium than, say, chromium, even though they're only one space apart. That is, we get greater consistency in properties down a group than we do across a period. So, the periodic table is often divided into metals, non-metals, and semi-metals. Sometimes the semi-metals are referred to as metalloids. The left 2/3 of the periodic table makes up the metals, and they are separated from the non-metals by the semi-metals. And the semi-metals kind of form this sort of staircase line heading down here, and they're these guys that are touching that line. There we go, those guys in there. Okay, so yeah, that's it. So most of the elements on the periodic table are metals. We have a few non-metals and even fewer semi-metals. So the metals have some distinct properties. At room temperature, all of them are solids with the exception of mercury, which is a liquid. All of the metals are shiny. They have a metallic luster. They're good conductors of heat and electricity, and we can stretch them into wires without breaking them. That means that they are ductile, and they can be pressed and bent into complicated shapes, which means that they are malleable. So this question from the book asks us, based on its location in the periodic table, do you expect indium to be a non-metal, a metal, or a semi-metal? So, all of the non-metals are to the right of the staircase line. Here it is here. So we can be pretty convinced that indium right here is not a non-metal. So then the question comes, is it a semi-metal? Well, it's 1, 2, 3 spaces away from the staircase line. So it can't be a semi-metal and it must be a metal. Okay, there we go. Now, some of the groups have trivial or common names. For example, the metals that are in group 1A are referred to as the alkali metals. The metals that are in group 2A, they are referred to as the alkaline earth metals. And you should know these names. As we mentioned previously, elements 58 through 71 are removed from the main body of the periodic table and put beneath it. Similarly, elements 90 to 103 are also removed from the main body of the periodic table and placed underneath it. These elements are in rows 6 and 7 of the periodic table. The elements that come immediately after lanthanum, they are referred to as the lanthanides. And the ones that come immediately after actinium, they are referred to as the actinides. And just a little piece of fun information, all of the elements that are in period 7 are radioactive. So you probably recognize elements like uranium and plutonium. The nonmetals occupy the upper right corner of the periodic table, but also include hydrogen, which is normally placed on the left of the periodic table. The nonmetals also have unique properties. In particular, the ones that are solid are dull and brittle. They are all poor conductors of heat and electricity. Most of them are solids or gases at room temperature, and only bromine is a liquid. So, all of the elements that are in group 8A of the periodic table are gases. The members of group 8A are known as the noble gases because under anything other than exceptional circumstances, they don't interact with other members of the periodic table, kind of like how kings and queens don't normally interact with the general public. If you want, you could say they are the snobs of the periodic table. An older name for the noble gases is the inert gases. Group 6A, or sometimes referred to as the oxygen group, is sometimes known as the chalcogens again. All of these elements in group 6A are solids except oxygen, which you probably recognize as being a gas. Group 7A are commonly known as the halogens. The first two members are gases. Bromine, as we mentioned previously, is a liquid, and then iodine and astatine are both solids. Astatine is very, very rare. Group 5A are known as the pnictogens. Nitrogen is a gas. The rest are solids. Interestingly, bismuth is the last non-radioactive element in the periodic table. Now, the metalloids lie on that staircase line that separates the metals from the non-metal. So we've got boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. And they tend to have properties that are in between those of metals and non-metals, intermediate properties. And all of them are solids at room temperature. So, kind of putting it together, we would like you to know these things about the periodic table. We'd like you to know that the elements that are in group 1A are referred to as the alkali metals. Those that are in group 2A are referred to as the alkaline earth metals. The elements that are in the B groups are referred to as the transition metals. Those elements in group 7A are referred to as the halogens, and those in 8A, the noble gases. If you could remember that the elements that come immediately after lanthanum in row 6 of the periodic table are referred to as the lanthanides, and the elements that come after actinium in row 7 of the periodic table that are placed underneath are known as the actinides. Then you might earn yourself some extra credit. The elements that are found in the S block and the P block, or what we sometimes call the A groups, are collectively known as the main group elements, and you should know that. So, we said that elements that are in the same group in the periodic table have very similar properties. And there's a good reason for that, and that's because that elements that are in the same group have the same valence shell electron configurations. And we can see this if we consider how the electron configuration of an element varies across the periodic table. Every member in group 1A will have one outer electron in an s subshell. Therefore, they're going to kind of look similar on their outer surface. Every member of group 2A will have two electrons in an outer s subshell. And then every member in group 8A, all of those noble gases, well, they're all going to have 6 electrons in an outer p subshell, and so on and so forth. So this is an example exercise from the book. So we're asked here to, using the variable n, to represent the number of the valence electron shell, write the valence shell electron configuration for each group. And the first one is asking us about the halogens. So the halogens are the fluorine group. And what we need to recognize, if we were to write out the valence shell electron configuration, let's say for a fluorine, would be that we would go 2s1, 2s2, 2p, 1, 2, 3, 4, 5, 2p, 5. Now we're asked to use the variable n to do this, so being generic for any halogen, because they all have the same valence shell configuration, regardless of the row of the periodic table, the electron configuration would look like that. So now we're going to do the same for the oxygen group. And we're going to think the same thing. Here's oxygen here. Go across here, 2s2, then we go into the p block, 2p1, 2, 3, 4. Now we're not asked to do it just for row 2, we're asked to do it for any row, just for a generic element in that group, but we know they all have the same outer electron configuration, so we can just make that ns2, np4. And there we are, we've answered the question. So the periodic table, because it's organized with elements that have similar properties closest to one another, means that a lot of properties vary systematically across the periodic table. For example, the radius of the atoms increases from the top right down to the bottom left between fluorine and francium, so F to F. So that's a cool little trend to keep in mind. And so what is the atomic radius? Well, it's normally determined by measuring the distance that is halfway between two atoms that are bound together, two identical atoms bound together. It's normally measured in picometers, which is 10 to the negative 12 meters, so it's very small. And a typical distance would be similar to that like observed in a hydrogen molecule of about 74 picometers between two identical atoms. So that means that the radius of a hydrogen atom is about 37 picometers. So the question becomes, why does the radius get larger as we move down and left across the periodic table? Well, hopefully you remember that every time we move down a row in the periodic table, we add another layer of electrons. So it's hardly surprising that the atoms get bigger as we go down, because each of these atoms has an additional layer to itself. You know, it's like adding another layer to an onion. As we move across, the atoms get a little bit smaller left to right. And the reason is while we are adding electrons to this same shell, that's not going to make the atom get bigger. But as we move left to right, we are increasing the number of protons that are in the nucleus, and that causes all of the shells to get sucked in a little bit and decreases the atomic radii a little as we move across a period. It's not a very big trend, but it is observable. So we can use the periodic table to rank atoms in terms of size, and that's what this exercise from the book is asking us to do. So it says, using the periodic table, which atom is larger? So we just need to remember that the trend is fluorine to francium getting bigger. So we have lithium here, we have fluorine here, and clearly lithium lies to the left of fluorine. They are in the same row, so that's not really a factor. Now we're asked to compare sodium and potassium, and we know that as we go down a group, atoms get bigger, so therefore potassium must be bigger than sodium. Okay, and so that concludes chapter 2.